Okay, folks, moving right along. Let's talk about the energy solutions now to the particle in a box wave function. And I expect this one will be fairly short since I've already presented what those energy solutions are. We just want to flush those out in a little more detail. So let's go for it. So once again, back to our wave function that we determined for the particle in the box. And there's actually a couple different ways we could arrive at the energy solution. We could go back just to the old classic solving the Schrodinger equation for its eigenvalue. Or, as I presented earlier, we could look at the expectation value of that superposition of the momentum squared and plugging in our result for momentum squared divided by 2m gives us the energy solution. So we can get the same energy solution in multiple ways. And what I want you to note here, it depends on the square of the quantum number, which I've kind of alluded to in previous lectures. So now if we look at our values of n here, we recognize that each specific value corresponds to a quantized energy solution. The values that are in between, these shaded values, those are those classically allowed values that we might expect from, our ball bouncing back and forth in our box. So remember, we can only get these quantized solutions when describing objects of small mass and energy, like an electron. So if we look at the difference in energy levels, right, that is what we are most interested in spectroscopy. So we can come up with this equation, En plus 1 minus En. And I'll also refer to that as delta En plus 1. So that's just looking at the difference between any one level. So we substitute n plus 1 into n right there. And so that becomes n plus 1 all squared times h squared divided by 8ml squared minus our original energy solution. And of course, we have to do some foiling there, right? We have to take the square. And doing some algebra, we end up with the following result. 2n plus 1 times our h squared over 8ml squared. Okay. So now if I plug in any value of n into this equation, that corresponds to the lower level. So for example, this one that I highlighted here, and of course I picked, a bigger number, so that's going to be tough math for us to do, but I think we can do it. So let's plug in n is equal to 6 into this factor. So that's going to be 2 times 6 plus 1 times this factor right here. So that gives me a factor of 13. Well, now if I look at this difference from 6 to 7, 49 minus 36 gives me 13. Okay, so you can see that the factor here before is what raises us up from the lower level of n to the next level up, n plus 1. We can do another example right here. So let's pick on the differences between level 3 and level 4. If I take 2 times 3 plus 1, that gives me 7. And we can see now on this relative scale here, the difference between 9 and 16 is 7. So each successive level spreads out as we go up, and that is based on the square, as you can see right there on the left. Okay, so we'll play with this energy solution more and talk about its outcomes in physically realistic systems. Okay, I'll see you in the next one.